Good afternoon. Tonight or this afternoon, we are going to emphasize a chapter that we have dismissed earlier in the semester, but we need to fill the gaps. The last time, as you remember, I'm in the wrong course here. We went all the way to the bottom of the curriculum and covered the solar storms, but we have left here earlier in the semester the concept of risk and safety ethics. And I'd like to cover that chapter today, being also on a Friday, so that would be an easy one to consider. If we deal with risk or the safety of engineering systems, as I suggested earlier, we become public servants. We become servants to the public in the sense that we uphold the highest principles of professionalism in terms of dealing with safety. So what are the very general concepts associated with ethics in the engineering practice when it pertains to risk? It is not a course on ethics. There is a course, in fact, by Professor Michel in electrical engineering that dedicates itself to the ethics in the engineering practice. You may like to think about it. However, in terms of safety only, you'll find that risk that we defined earlier as having to be anonymous, that has to have meta-uncertainty, that it's a prediction before realization, and so on, has other characteristics in terms of how we deal with it as professionals. And we deal with it first individually in terms of ethics, and we deal with it also through the laws of the land. And the third aspect is the professional societies like the IEEE, for instance, the American Society of Mechanical Engineers, the American Nuclear Society, and the ABET organization, which is the Accreditation Board for Engineering and Technology. We get visited every 4 years here on campus, different departments to be accredited, and they review the levels of coverage in terms of the professionalism in the engineering profession. And they accredit our courses or our programs, different departments, and you'll find that this is also the organization that we learn about that would give you, after you graduate, you take an exam as a professional engineer, and you get better, higher salaries and higher probabilities of employment in general. So if we talk about risk in the engineering, it covers all our structures in our society, products, processes, and materials that are used in the construction and operation of any engineering structure. Invention and innovations are part of it. And when we innovate or create new systems, we introduce an extra element of risk. In what? In the lack of knowledge about how those innovations or new structures, new design for a car, for instance, is going to reduce risk or increase risk. Examples that we deal with today is fires caused by damage or overheating that initially occurred in the introduction of lithium-ion electrical batteries. Some people would use, we all use, in fact, lithium-ion batteries on our laptop computers, in the early designs of those batteries, they would simply heat up and simply catch fire. That is not happening anymore. Cellular phones also dealt with the same problem. Why? Lithium is extremely reactive with the air, the same as sodium. And in that case, you have to isolate it from the air. So if there is any manufacturing damage, a crack, maybe a phone falling on the ground can damage the batteries, and lithium is exposed to the air. In air or in water, lithium is reactive and would catch fire if it doesn't lead to even an explosion in that case. So the whole idea also spread to the General Motors early electric car. They had what was called the Volt electric car by General Motors, and it's still there with the Tesla cars. And at some point, some airplanes, the Boeing 787 Dreamliner airplane, had a problem also with those early lithium-ion batteries. And in airplanes, it becomes a very serious situation. And it did happen in that some of the lithium-ion batteries newly introduced to airplanes, to the auxiliary power unit. The auxiliary power unit on an airplane is a unit that you would hear. In fact, if you go on an airplane, you find some generator running, and that generator provides power to the plane before the engines start rotating. And then in that case, the airplane gets its power from the rotating engine. So this is called the auxiliary power unit in a very new design, the 787 Dreamliner in Japan Airlines on January 212. You'll find that here is the batteries. You could see the damage here. They caught fire. And of course, you don't want that to happen when the airplane is up in the sky. So newly introduced technologies has associated sometimes with no risk. This is not pie in the sky. This is a testing of the Volt electric car that was introduced initially by General Motors as an electric vehicle. They had the battery at the bottom of the car, and if you hit it, you damage the little batteries that are made out of lithium ions. Lithium basically in association with some alloys like manganese and cobalt, and as those batteries are damaged, this is a testing of one of those Volt cars. You could see that the whole thing basically catches fire. And the reason is this. It is. You could see that the battery there is at the bottom of the car, in between the drivers and the passengers at the bottom. And it was very simple to fix the problem. The problem was fixed by adding 2 side poles to prevent those batteries here in the center of the car from being damaged in the case of a collision or hitting some object, in fact, on the highway. And this is a situation with the not to be undone by General Motors, the Volt car. This is a Tesla car now, and it was driving on the highway. The bottom where the batteries are, lithium-ion batteries again, basically hit a piece of metal on the highway. And you could see that the whole battery now starts getting on fire. The firefighters came in and they didn't know that lithium is reactive with water. So they go and try to extinguish the fire with water. Oh, they make it even worse. So this is a new technology basically that is introduced, and we have to deal with it in general. To ensure accounts, so of course, this manufacturing and the batteries are being replaced, and we can look at that for if you study electric vehicles. Go to our class on energy storage systems, you can read more about it. To ensure comfortable safety levels, engineers, I'm not saying should, but I'm saying are obligated. This is an ethical obligation. We have to protect members of the public. So in that case, we have to anticipate or try to predict all the failure modes that any new technology that we introduce can subject any member of the public or potential users. And once the new technology is adopted, then we have to follow the operational experience, and that includes nuclear power plants, it includes electrical vehicles as new technologies, computers, phones, even use lithium-ion batteries and so on. Now, as engineers, we are bound, we are obligated by law. First, the law of the land tells us that we should do that, so we have to abide by the law, or we'll be breaking the law, we'll become criminals. And professional ethics, that's of course professionalism and ethical behavior that amounts to a high level of responsibility that is assigned to us if we are given the responsibility of the safety of our engineering products. So we have to adopt the concept of what's called informed consent. And that concept of informed consent is not part of the law as much as it is part of the ethical and professional behavior. And this has to do with any risks that is involved in our designs, being airplanes, being wind turbines, nuclear reactors, and our projects in general. The penalty for being uninformed about the laws pertaining to risk or failing to follow them could be litigation, meaning that you find yourself going to the court system, and people, when they are damaged, and they don't lose their life, but even their next of kin would intervene if they lose their lives. They'll ask for damages. Look at this gentleman. You read about that gentleman who denied some kind of a shooting that happened in his school, and the courts are fining him to pay the parents of the kids who died in the shooting that he denied happened $1 trillion. So he's totally bankrupt, and he has no way in society to survive anymore. The United States society and its democratic tradition and institutions, a policy of concealing the discussions from the public is out of the question. And that happened at the time where the debate was about smoking. The companies that were making tobacco, basically manufacturing tobacco and cigarettes, knew that the nicotine and the benzoapyrene in the cigarette smoke can cause cancer, but they hid it and denied it for the sake of making profit. And in that case, they were fined, and the people who were in charge ended up, of course, losing their livelihood and losing their jobs. It is important to make safety decisions with contributions from the public. If we introduce new risks in a new technology, we have to get acceptance from the public by making the public aware that the benefit that we get from the new technology exceeds the risks that are associated with it. And that's why we had the cost-benefit analysis chapter, for instance, where the cost is some kind is weighed against the benefit of getting the new technology. Considering, of course, that experts themselves could be wrong in their estimates, so we need to inform the public about any risks that we have in our calculations. In that case, in all the engineering disciplines that you would belong to or practice in, because we don't know what your future is going to put you, you'll be dealt your own card to contribute to society. You'll find that the factors of safety and ignorance factor have to be introduced in all designs. And this is not something strange to you because you have seen it in different courses in general. So the engineering profession uses the concept of factors of safety or safety factor in our design processes in general. So if you have a member, like a beam in a structure, here the structure is all steel beams, you would have to consider a factor of safety as the maximum stress that the member, I-beam or a T-beam in the structure can take, and take the design number larger than the maximum load that the structure can take. For instance, if you have a beam that can take a stress or a weight of 1,000 kilograms. You don't go and design it for taking only 1,000 kilograms. If you take a safety factor of 3, you design it to take an unexpected load that could happen to it at 3,000 kilograms. So in that case, we call this the factor of safety. Usually it is 3, but some people may take it maybe 4 or 5 or 6, and we have to err. The error should be on the larger side, not on the lower side. In addition, you'll find that even when we design any kind of device, it is not just that we know what kind of loading, the circuit may be an electrical component, but we also have ignorance in the data that we are using. And most of the measurements in data in any engineering system is about maybe 20% in error. We cannot tell exactly what is the load that is it is subject to, whether the steel we are getting from maybe the factory has flaws in it. So we add to this what we call the ignorance factor. So we have to deal the factors of safety and the ignorance factors. That depends on the engineering aspect himself. For instance, if there is a distribution in the load, you take the maximum loading divided by the minimum load or the average value, or any unpredictable load values, or even unaccounted for emergency uses. And unfortunately, that wasn't the case in the Fukushima accident. They designed it for an earthquake level that basically was much less than what happened in reality. They took a historical value when, in fact, they had to go higher than the historical value. So that's what we call the ignorance factor. So in general, we modify the design value of any component we design by multiplying the factor of safety. Here I'm calling the safety factor or factor of safety by an ignorance factor I sub f multiplied into the maximum loading. In practice, you use for the safety factor maybe a factor of 3, and usually the ignorance factor is maybe a factor of 2. So if you know that your maximum load in your design is, say, 1,000 kilograms that the member can take, the yield stress in that case, you multiply it by the safety factor 3, and maybe the ignorance factor 2, so that becomes 6. And 6 is really a typical value that people use in any kind of design. So a beam that is expected to take a load of 1,000 kilograms is designed to take 6,000 kilograms in terms of our introducing safety factors and ignorance factors. And this is, in fact, a professional kind of value. Of course, you don't go and just design it for 1,000 kilograms. It will be cheaper, but you'll be subjecting members of the public to accidents that are not needed in that case. You find that you are bound in that case as engineers in the engineering profession by laws that pertain to risk. And we spend some time working on risk. There are numerous laws and regulations that pertain to risk. And you can find the laws in the, if you visit the main library on the other side of the stacks, you'll find that we have the reference library, and the reference library contains the laws of the land that and the regulation that we have to follow, especially if we deal with nuclear systems because of the possibility of radiation. But there are laws in all fields of engineering and science. For instance, there is a 1958 Food, Drug, and Cosmetics Act. It mandates that a chemical code deemed to be unsafe may not be added to food until it is can be safely used. The concept of safe use was defined by the United States Senate Committee on Labor and Public Welfare as meaning that, quote, no harm will result from its addition to food. And you find that lots of foods, of course, have coloring added to it. Yellow sometimes looks nice. Red coloring looks nice. If you buy salmon from the store, they add that nice orange hue, which is not really the actual color of the fish, but they have to prove that the coloring is not harmful in any way. There is a law called the Delaney Amendment. It prohibits the addition to food of any chemical known to cause cancer when ingested in animals. Why is that? Because at some point they added some chemicals that have nice coloring, but they were really carcinogenic and terragenic, meaning that they can cause, they get cancer initiated just because to add beautiful color to food in general. In 1976, Toxic Substance and Control Act, the name is TSCA, asked the Environmental Protection Agency, EPA, to regulate any chemical upon a finding of, quote, unreasonable risk or injury to health or the environment. And TSCA requires us as engineers to take, quote, the availability of substitutes for the substances that could cause risk. The 1954 now Atomic Energy Act refers to risk in terms of the health and safety of the public. And this is our emphasis in our, of course, our course, since we are dealing with nuclear systems in that case. The laws of the land are taken care of or managed by the Nuclear Regulatory Commission. And in that case, they use the without undue risk quote and suggest a balance between risk and benefits. And that was the incentive for us to cover a whole chapter on cost-benefit analysis. If we do not follow the laws, we become, in that case, liable. We face dismission from our professional societies, so we cannot be employed. And you hear, for instance, about the medical profession being very careful there. If a doctor does not follow the covenants of the medical profession and he causes harm to people, then basically the board, the medical board will fire him and he cannot get employment. Same for engineers, as a matter of fact. You have to show for any employer that you don't have any history of breaking the laws of the land. There is a law that is called the law of torts. If you haven't heard about it, it's some kind of a little on the legal kind of side. And the law of torts creates redress or seeks redress from harm, most commonly appealing to the law of, if somebody is harmed, he appeals to his attorney in that case, or his lawyer appeals to the law of torts. And this law deals with injuries to a person caused by another, usually as a result of negligence or fault of the injuring person. And this is almost very important. If you own a car, you have liability insurance, all right? So if you cause harm to somebody else, you have to pay him damages because he may have to go to a hospital and his livelihood may be affected. He loses his car maybe. So in that case, the law of torts applies right there. An example of the law of torts is a litigation that from the harm caused by asbestos. Asbestos is a mineral, in fact, that occurs in nature, and it occurs in the form of fibers. And if you go to the old buildings, even if you go just to Talbot Lab, not far from here, you'll find that the pipes have an insulation around them because we get steam from the steam plant at the southeast side of the campus. It's a coal and natural gas plant. And the steam circulates in those pipes. You find that they have an insulation around them. And unfortunately, they use that asbestos. Asbestos is a very, very good insulator. It's a mineral that is mined from the ground. However, when that asbestos wrapping around the piping fails, that asbestos fritters and gets into the lungs of people. I have been in an office for about 20 years where we had that asbestos piping. Of course, we don't have it in that building, so we are very well protected, but asbestos can cause asbestosis. It gets into the lung and causes a very nasty cancer for people who are subject to it. The company that was making that asbestos is the Fiberboard Paper Products Corporation, and it causes irreversible lung disease known as pulmonary asbestosis. And you'll find it sometimes also advertised on TV for people who have been assigned damages, but they don't know that they they can access that damage. The disease is called mesothelioma, and that's a lung cancer. And another example involved, and that company basically had to pay damages, so it went bankrupt from the amounts of damages that it caused. Another example is the use of polychlorinated biphenyls. You may have heard the word PCBs. These are kind of oils that were used in transformers, electrical equipment, and it is the most toxic chemical known to man, those PCBs or polychlorinated biphenyls. We had some students in the area between the radiation lab south of along Green Street, as a matter of fact, and they used transformers in the parking lot, and they opened them and spilled the PCB's oil, and then people walked in the oil and tracked it into the buildings, and they had to go and dig out all the ground to basically get rid of those PCBs. This is a lawsuit against the Whitco Chemical Corporation and the Monsanto company. That Whitco Corporation probably went out of business. Monsanto is still surviving in general. Other cases involve the exposure of paraquat. Paraquat is a herbicide that was used in Vietnam to deforest the forested areas so that troops can be seen and cannot hide under the vegetation. And what's called also the Agent Orange herbicide that is still being used, unfortunately, today. In tort law, the standard of evidence is, now that's something we need to remember here, the standard of evidence that the complaint is true or not true, or acceptable or not acceptable, is the preponderance of evidence, as it is called in law. This means that there is more and better evidence in favor of the plaintiff than the defendant. And it is a lower standard of evidence and is less stringent than criminal proceedings. If you go to criminal proceedings and you are guilty, the proof that you are guilty should go beyond reasonable doubt. And however, in the tort law, it is not beyond reasonable doubt, it's a preponderance of the evidence. If there is evidence that you have been harmed, it is a lower standard of evidence than the beyond reasonable doubt. And those demanded by the standards of proof in science we require another level, even higher than the beyond reasonable doubt. We need to have a certainty at the 95 percentage level. That goes to one standard deviation is 67% of the area under the normal distribution. So that's a mean value plus one standard deviation. Two standard deviation take you to the area under the normal distribution, which is 90% of the area. If you go to the 95%, this is the mean value plus three standard deviations. So this is really where we are bound in laws, tort law, and as well as in terms of preponderance of the evidence, or criminal law would be beyond reasonable doubt. We are also bound as engineers not by the laws of the land, but also by the rules of our professional societies. So in that case, professional societies has laws that we have to abide to if we want to practice the profession, same as the medical doctors. For us engineers, we have several societies, the National Society of Professional Engineers. Some companies will require you, as you accept a job with them, to take the test for the professional engineers, the National Society of Professional Engineers. And in that case, the code of ethics for engineers in general, what they call the first canon or first law, is to, quote, hold paramount the safety, health, and welfare of the public in the performance of their professional duties. So we are all bound by that law as professional engineers. It requires engineers to design safely in terms of, quote, acceptable engineering standard. Oh, that gets us back to that safety factor at that ignorance factor. If we design any kind of a component for in engineering, we have to add the safety factor and the ignorance factor. It encourages engineers not to complete, sign, or seal plans and or specification that are not of a design safe to the public health and welfare and in conformity with accepted engineering standards. The Accreditation Board for Engineering and Technology, you heard about that, ABET, visits different engineering programs at universities once every 4 years, and they review that indeed the professional engineers that are being educated have a knowledge of these basically norms of professional behavior and ethical behavior. It was named before the Engineers Council for Professional Development, and basically they have what they call the Code of Ethics of Engineers, and that is the National Society of Professional Engineers. You are all recommended, of course, once you graduate and you still have your classes in your mind, to go and take the test to get the degree of a professional engineer. They have fundamental principles. I'm not going to go over all of them. Engineers are bound in terms of integrity, honor, and dignity of the engineering profession to use their knowledge and skill for the enhancement of human welfare, being honest and impartial, striving to increase the competence and prestige of the engineering profession, and that's how you become a professional engineer. They have what they call canons, enunciated as engineers shall hold paramount the safety, health, and welfare of the public in the performance of their professional duties. And in that case, engineers shall continue their professional development throughout their careers and shall provide opportunities for the professional development of those engineers under their supervision. So this is our code of ethics and our responsibility towards society. I think the battery is gone. As professional engineers. Different societies also have their own rules of ethics. If you are an electrical engineer, you sign up to become a member of the IEEE. IEEE, I think, stands for the Institute of Electrical and Electronic Engineers. You'll find that to be a member of that society, you have to follow their own canons other than the ABET kind of rules to accept responsibility in making engineering decisions consistent with the safety, health, and welfare of the public. If you are a mechanical engineer, you join the American Society of Mechanical Engineers. If you are a nuclear engineer, you join the American Nuclear Society. Each one of those societies has their own laws, and you do not belong to that society unless you follow those rules. You commit yourself to these rules. We already described the concept of risk perception, and risk is not really totally it is not totally a science. There is an aspect of it that is really some art because of that perception of the risk. Some people, for instance, consider riding motorcycles as very risky, whereas some other people, they don't consider risky. Some people will go jumpy, bungee cord jumping out from bridges or from airplanes or whatever. Some other people do not consider it as risky. So for most people, remember, we define the risk as being equal to the probability of an occurrence of an undesirable event multiplied into the consequence. The probability has no units, so you'll find that the risk usually has the units of the consequence. And in engineering, we do not consider only one element of risk. We sum it over all the possible sequences that can happen in an accident, and sum it over all the possibilities of accidents or the undesirable events in an engineering system. For most people, you'll find that risk is perceived differently, and it involves other factors like the equity of risk, meaning that is it equitable for people involved in some activity to be exposed to the risk, say to chemicals, maybe in a chemical process in a factory. Sometimes the perception of risk is dependent on the control of risk. For instance, we prefer to drive our own cars on long trips around Thanksgiving or Christmas, visiting our friends or family. And in that case, we prefer cars to airplanes. And why? Because we have control on the risk when we drive a car. And in fact, flying by airplane is less risky in terms of accident than it is with cars. So that is a perception. And of course, sometimes it has to do with the understanding of risk itself. So in that case, we have studied already some of the risk assessment methodologies. We studied in detail fault tree analysis. We are not going to get into that again. We studied event tree analysis, and we studied cost effectiveness analysis in general. With all what we have studied so far, still there are limitations to the occurrence of risk itself. We suggested that we can use probability theory when we have data available to us. And if we don't have data, we can adopt possibility theory, and we know the difference between them. Notice these are exact analytical mathematical approaches that quantify the uncertainties. In probability theory, the uncertainty is the randomness of the events that occur in life. And possibility theory, it is the meaning that we give to those undesirable events like hot, cold, risky, safe, and so on. The successful application of these methodologies that are theoretically exact mathematically must recognize their usefulness as well as their limitations. They have limitations. One cannot claim to be able to fully anticipate or to predict all the mechanical, physical, electrical, or chemical initiating events that can lead to the failure of the components of a complex system, nuclear reactor, or a bridge, or a train, or a refinery, or all of these. We cannot claim that we know everything. So there is always an element of uncertainty associated with it. And then it means that when we calculate risk, we have to associate it with a meta-uncertainty, meaning that we have to say, okay, this is the value plus or minus the error factor in that case. We have to consider the possible human errors that can lead to failures that cannot all be anticipated. And this would be an example that we'll study in the 3 Mile Island, the Chernobyl accident, as well Fukushima. Human error can occur, and it's very hard to predict human error because most of the time it is not really, it is unintentional. And it depends on the model that we use in designing those systems, which can contain their own deficiencies or own errors. Our remedy in that case, as I suggested all the way at the beginning, is to adopt those safety factors as well as those ignorance factors. Despite the existing limitations, the responsible engineers must try to anticipate. We have to do prediction. Remember, risk is associated with a prediction. And once, if the undesirable event happens that is anticipated or predicted, it is not risk anymore. We call it in that case an accident in that case. Once operational, any system must be monitored and controlled in such a way that the performance levels of the individual components, and we define performance level as our own type of contribution to the field or research, the performance should be continuously monitored as we operate the devices that we construct or build for society in general. So the system should thus be steered away from any undesirable future states to a favorable state all the time by our control systems. Just reacting to the occurring malfunction should be replaced by prediction and avoiding its occurrence altogether at the design stage in general. All right, we dealt already with risk-benefit or cost-benefit analysis, so I think we gave it its due need, and we need to understand the concept of risk values and orientations. Why is that? Because in the United States, we have a very, very, very different perspective from our friends in Europe in terms of considering the responsibility that happen from undesirable events. So you'll find that there is a concept that is called the level of acceptable risk. It defines a professional and ethical dimension of the engineering profession. There are two sets of values, biases or orientations in the definition of risk and orientation. There is what's called the good science approach, and there is the respect for persons approach. And we need to understand fully the difference between them, because sometimes we find ourselves dealing with components, say, that are manufactured in other places all over the world, from China, Japan, Europe, Germany, France, and different countries have different conceptualization of how to define risk. So the good science approach, one avoids the prediction of hazards to the public health and safety where none do in fact exist. And the burden of proof, remember that very carefully, the burden of proof of the existence of a risk or a postulated risk is on those who claim that such a risk could exist. It protects the rights of producers of new technology and avoid burdening them with excessive regulations. This approach evidently promotes innovation and economic growth. And that is the approach, I remind you here, and remember that all your professional life, this is what we adopt in the United States. So in that case, the people who claim there is a risk has to prove that the innovator or whoever is generating the risk, in fact, is generating risk. So that's what we call the good science approach. And the approach here that is adopted in the United States, as I suggested, basically favors corporations that innovate. And that's why we have Google, we have the Apple computer, we have companies that innovate, whereas in Europe, you'll find that Apple computer companies and Netscape, for instance, or Netflix, sorry, do not arise. Why? Because the Europeans have a different philosophy. They have the respect of person approach in terms of looking at risk. In this restrictive approach, one attempts to discover as many threats to the public health and safety as possible and incorporate them in the design process. And for instance, Tesla never thought when they developed their electrical vehicle using lithium-ion batteries, then they'll catch fire. They went and built the cars, and they became part of the manufacturing process without testing it. In fact, the situation with vaccines, what they call vaccines, they changed the name of the mRNA, which is messenger RNA. They are really more or less, some people suggest they are, as I have been reading, they are really more like genetic treatments. They're not vaccines. They don't get the vaccine, the virus itself, and kill it or make it less virulent and then inject it into us. That's a totally new technology, and it was used, and we have been forced to use it. So we became, in fact, guinea pigs, but it led to innovation. That's a new way of dealing with viruses in general. So in that case, the burden of proof is shifted to those who claim that say those vaccines are causing them heart inflammation or that it's causing clotting in the blood, not to the companies that have introduced the vaccine. So the respect for persons would be the approach that is followed in Europe. If people there complain, say that some insecticides are killing the bees and they're getting in the environment, they basically, the companies making those insecticides have to prove that that is not the case. So it's a very, very different approach. Our approach in the United States favors innovation. The approach in Europe and Russia, in fact, in Japan too, favors more like the protection of the public. In our case, in the United States, we get more innovation. We get new products that would not basically rise to become main products in these other countries in general. According to this ethical perspective, and we have to understand it thoroughly, it is wrong to deny the moral agency of individuals. So individuals count more let's take European society compared with our society in the United States. Is basically society at large benefits from the innovation by our companies and corporations. So in that case, we talk about moral agents are defined as being capable of formulating and pursuing purposes of their own. And they talk about moral agencies protected by rights to life, health, physical integrity, not to be deceived, as well as the right to free and informed consent to risks that could infringe on these or other rights. two very different approaches to the values and orientation in terms of risk. And you may have never thought about it, but simply check it out in real life during your careers in general. We have a principle of acceptable risk. So that is a principle that we can work on in terms of innovation and introducing new products into the engineering profession. The principle of acceptable risk has been introduced by Harris, Pritchard, and Robbins, who wrote a book really in the references that you can read. And basically, they define the concept of acceptable risk as follows. I give a quote here. People should be protected from the harmful effects of technology, especially when the harms are not consented to or when they are unjustly distributed, except that this protection must sometimes be balanced against two things. First, the need to preserve great and irrepressible benefits, and B, the limitation on our ability to obtain informed consent. So that is our view in the United States, and it's not necessarily the same as in other parts of the world. That raises the concept of the doctrine of informed consent. So if we introduce risk in any products that we are responsible to introduce society, we have to get informed consent from the public, and we have to get acceptance from the public in general if we introduce risk in our product. There is a disparity that exists between the expert's opinion, us as engineers in that case, and members of the public. And that's why sometimes technologies are some kind of opposed, because there is some effects from psychology in that case, or human factors that it's called, the whole field of psychology, human factors, which is called the anchoring effect. Behavioral psychology study the phenomenon called anchoring. People tend to take recent events and projects and project them into the future in a straight line. We anchor our projection on some number or data we have recently seen. Tomorrow will be like today in general, and that's the way we look into the future. Maybe it is true, maybe it is not true. There is another effect from psychology, is the voluntary versus involuntary risk effect. When we are in control of the risk, when we drive our cars on the highway, we are at risk of accidents. Because we are in control, we accept a higher risk than if we take airplanes, which are less risky. In reality, if you take the statistics on how many people are affected by plane accidents compared to how many people are affected by car accidents. There is a compensation effect. People try to accept a higher risk if you compensate them accordingly. So the fact that you say that the level of risk in accepting risk, people are willing to accept in the workplace is proportional to the cube in the increase of the wages that are offered to them. And that's why you find, for instance, nurses or medical doctors working in hospitals are at risk of catching the diseases from the patients, but they accept the job. Oh, why? Because they are compensated accordingly. As an engineer, you would make, say, 70K as you graduate, but an MD gets 250K, same as nurses, for instance. There is also an effect of a human-made risk, cars and planes, against natural risk. We tend to accept the natural risks more than we accept human or man-made risk in general. Timeliness is an effect. An immediate risk is perceived as being, psychologists tell us, 30 times more risky than a risk that is in the future. And we also, people in general, consider that a catastrophic risk versus regular risk are also taken more into perception, or they're perceived as more dangerous. For instance, the risk from a hurricane that's catastrophic, it's not the same as living in an area where you have mosquitoes, say, that's a long-term risk, or the risk from getting black lung disease in mining coal, or getting radon gas in mining uranium. In fact, there is a difference in our perception of risk, regular versus occasional risk too. And sometimes risks are necessary versus luxury. We don't accept, of course, any luxury risks. We only accept risks that are necessary. That leads us to what's called the precautionary principle. As I suggested back again, it is different in the United States compared to other countries in the world. And since we are going to be international citizens as engineers, we'll work all over the world, we should be aware and respect that precautionary principle. In most Europe, the precautionary principle is adopted. Remember that. So you don't go there and fight the Europeans. That's their own culture. We have to respect their culture in the same way that they respect our culture. It suggests that when there is enough data to have a suspicion of harm, one can go ahead and act without having to have absolute proof of harm. That's why some herbicides like neonicotinoids, for instance, they come in from nicotine, are banned in Europe, but they're not banned in the United States. And the same company that makes it, this is the, I forgot the name of the company. Yeah, here it is. The company is, let me see. The neonicotinoids is made out of, I forgot the name of the company. It sells it in the United States, and they make $700 million per year selling the neonicotinoids that are killing bees, but in some European countries it is banned. So in Europe, the precautionary principle is adopted. In the United States, we basically don't have it, and we favor innovation by the corporations, and that's an advantage to our society in general. In general, we have to think in terms of the ethics of engineering. We have to take those 4 considerations that I'd like to just read and end up the lecture and wish you a nice weekend. First, we have to be aware of the awareness of uncertainties as well as the value dimensions of the different phases of the analysis of the treatment of risk that we have to make available to members of the public. We have to be aware of the limitations, even of the method that we use, cost effectiveness analysis, for instance, fault-free analysis, event-free analysis. We have to promote the democratic and free informed consent of the members of the public. We have to tell them the truth about risk, and we have to develop our abilities to think competently and clearly about the ethical aspects of risk in general. And I invite you to read more of the detail of risk and be an ethical and professional person in our careers, all of us. And thank you, and have all of you a nice weekend.